So hello everyone, thank you for coming back again to the Hardware City channel. Today I want to proceed with some project I am postponing since I don't know when, at least for years. And it was a first approach of making some prototype of a very sensitive magnetic field sensor, measuring the flux of the Earth's magnetic field. It's quite a bunch of years ago since I made this little project, and I had quite good resonance on YouTube, and I wanted to bring this project to an end, but there were so many things coming across my way, like programming languages like Oberon and other hardware stuff, so it's still not completed yet, mission not accomplished. Now I want to show you that I'm still proceeding with this project, and I made a new circuit with no software, the real pure hardware solution, and I want to show you how it works. Okay, this is my breadboard. Well, it's a little narrow here because all here in my shack is lacking space, but let's see if this is getting us anywhere here. Okay, so here's this, the circuit, here's the schematic. I'm going to explain you later. This is all the electronic stuff, and here you can see my magnetic sensor made of a motor drive that is turning this second motor, which has no casing. That means that the lines of magnetic flux are going through the rotor coil and are picked up as a voltage when the motor turns. And this signal here is amplified and processed. And here, this red diode you can see here is just a visualization, because in the final stage it will be replaced by a small transmitter. I hope you may remember the TX-SIW433 transmitter I showed you in one of my first videos on the Hardware City channel, and this will come into function here. The case is that the strength of the magnetic flux that is measured is transmitted via the transmitter as a pulse with a variable length. That means a short length means a high proportion of magnetic flux, and a long impulse will be representative for a small amount of magnetic flux. But we're gonna dive into this topic in more detail a little later. So I switch on this now, and you should take care of this motor sensor and of this diode that is indicating when the transmitter is going to be switched on and off. So at first nothing has happened. This is because I have a timing circuit here that turns on this whole stuff for taking measurements about every half a minute. This is specified by this capacitor here. I'm going to show you this in more detail in the schematic. Okay, now let's wait and take a look at this red diode here. In short, yes, you see it lights up and goes off again, and now the motor is turning on, and after a while the transmitter diode is going high again, and then it gets all off. Now, okay. This the cycle is repeated about every half a minute. Can be specified by this capacitor. And now I'm going to explain you in more detail what's going on here. Okay, let's see. So this is the schematic here. Everything this electronic device does is managed here, and everything is done pure in hardware. Here you can see the core circuit. Of course it's an NE555, which is responsible for the timing of the measurement which has to be taken. And you can see here something that should look familiar to you, because I use this also in my very easy analog to digital converter for measuring daylight. This is a self-triggering circuit here for the NE555 with a capacitor here and the resistor network here. And while the capacitor is slowly charging up, you can see that this point here, the voltage on this point is moving down very slowly, and it's connected to the trigger input of the NE555. So after a while, when the capacitor has charged up, this point here is becoming so low that the lower trigger level is reached and the NE555 triggers. And what it does is that the output here on pin 3 is getting high. And via this diode and this resistor here, the capacitor is recharged in a very short amount of time. And as you know, the impulse length of the NE555 output is specified by the charging time of this capacitor here. And this capacitor takes its time for charging from the current it gets. And the current here is provided by a constant, well, more or less constant current source. It means it's a current source where the current is specified by the voltage, because this here is an PMP emitter follower, you can see, and it's acting as a current source. As you vary the voltage here on the base of the transistor, more up and down, the current flowing to the capacitor becomes more or less depending on this voltage here on the base. And the voltage on the base here is specified by this amplifier unit here. This amplifier unit is a simplified outcome of my first amplifier I used for measuring the magnetic field. I have less stages of the amplifier now as I had in my first approach. You can see this one here is a standard amplifier that works to get intermediate ground voltage, which is lying between the original ground and the supply voltage. This is a standard circuit for generating this this artificial voltage to specify the idle point of the amplifier. And this here, the amplifier itself is very simple. It's an amplifier circuit used with a high impedance input. You can see this here is the pickup coil from the magnetic sensor, and it's going through this resistor and this capacitor, working as a low pass filter to filter out the switching spikes of the motor collector. It's going directly to the positive input of the amplifier, and the feedback network here is a 220 kilo ohm in series with 1 kilo ohm, with the connection point wired to the negative input of the amplifier. And so this is an amplifier that gives a maximum amplification of about 220. And here you have an additional fork with a potentiometer, where you can apply a pre-selected voltage to the negative input. This is for biasing the amplifier in a way that normally, when no signal is applied, the voltage on the output is about 3/4 of the supply voltage. So that means that finally the base of this transistor, the bias of this base, is directly placed in the middle between the voltage here, that's the ground voltage of the amplifier, and the positive power supply. So this is the point right in the middle. So you can get a symmetrical output swing of the applied current. So what happens here essentially is nothing more than, depending on the strength of the magnetic field which is measured here, which specifies the output voltage of the amplifier, the current is following this change proportionally. So in the end, the net effect is that the charging time of this capacitor here depends on the measured magnetic flux. This is what we want, because we want an output pulse of this unit, which duration is proportional to the measured magnetic field. So, but what is this stuff here? This stuff is a pure hardwire logic made circuit to get all this, to make all this control stuff. So when this NE555 here is triggered, you can see that the output, the high going output, is routed here to this NAND gate. And the NAND gate has two inputs. One is directly connected to the output of the NE555, the second one via a capacitor and a resistor to ground. What happens here is when the capacitor is charging, both points here are more or less on the same level. That means we have high on both inputs. When we have high on both inputs initially, the output is going low. When the output is going low, then this capacitor is prevented from charging because the charging current is routed via this diode to ground in this NAND gate. So that gives a delay. For what do we need this delay? Well, it's very simple. We need a delay because it's not a good idea to start the measurement directly after switching on the motor for the sensor. This is because, as you know, the motor has a mechanical mass that needs to be accelerated, and this takes some time until the motor or this whole compound reached its specified RPM. So just after a few seconds the RPM of this driver unit is constant, and only if this RPM is constant you can do your measurement, because otherwise you would screw up your measurement values. So this time is taken for the motor to settle down to, or settle up to this specified RPM. And when this capacitor here is charged, then this point here is going to low. When you have a low and a high level on a NAND gate, that means the output is going high again, and this capacitor is released. So at this point the charging really starts. The second thing that appears here is that at this moment this latch flip-flop is set, because the output of the NAND gate also goes here to the clock input of the flip-flop, and the data input is wired to high, hardwired. So when the flip-flop is set and the output is going high, then you can see it's directly driving the modulation input of the transceiver, the TX-SRW433, and the transmitter is going into action, starting transmission. When the voltage is going down again after the measurement process has finished, as I told you, we have a voltage here depending on the measured magnetic flux, and that depends the current here going into the capacitor, and so it takes some time for the capacitor to reach its upper trigger point, which is 2/3 of the power supply here. When this point is reached, then the NE555 switches down again. When it switches down again, the signal here is going through this NAND gate, which is working as an inverter. So when the 555 is going down, this signal is going up, and this flip-flop is resetted, and also the modulation of the transmitter is going down. The last fork here is something very special. As I showed you the first time, you saw a short blink of the red dial. That means the transmitter was going into action, but the motor was not running. Why is it so? This is a trick I made, because that means before every measurement of the magnetic flux starts, I'm doing something like a reference measurement. That means I'm doing a measurement without kicking the motor into start. what happens if we do so? What we then do is take a measurement value from this amplifier here with a sensor input of 0. So that means you get the 0, the reference point of the system that tells you this is the voltage reference point when no sensor signal is applied. And this reference signal is a very cool thing because you can relate all your measurements to it, and you have measured out all those tolerances of the amplifier, of these resistors and capacitors, and also, what's really much more important, the temperature dependencies of all those components. Especially here the electrolytic capacitors have a tremendous temperature dependence, and all this is zeroed out by getting this reference value. So that means that the target system, which is a computer, takes both value, at first the reference value and then the real magnetic flux value, and can put this into relation. And so all errors are zeroed out. And this is done here, because as you can see here, every impulse of this NE555 is going to the clock input of this second flip-flop here. This is, by the way, a second flip-flop which is contained in the same casing like this one, because this is a 4013, which means we have two data flip-flops in one casing. And the input, data input of this flip-flop is wired through the negative output. When you do so with a data flip-flop, that means you get something of a toggling behavior. Every time you apply a clock impulse, the output of the flip-flop changes. So that means the first impulse that arrives here is setting the flip-flop, and with these two NAND gates, which form really one AND gate, are switching on the motor via this driver unit. And when the second run is done here, and the second impulse arrives here, then this flip-flop is resetted and the motor is not started, but the measurement process is coming into place also. And that means we have our measurement of the reference value. So, I hope this is clear now. And now I'm going to show you something on my scope. Okay, now I put the probe of my scope right at this point here on the output of the amplifier, so you can see how the magnetic signal is measured. So you can see this is varying a little bit because you always have tiny changes of the RPM of the motor. And now I have my magnet here, and you can see when I'm coming close to this pickup coil, the signal changes in one direction or even the other. It's very sensitive. Okay, and now I put the probe to the capacitor here, so you can see the rising voltage. Did you see it? Voltage was going up and until it reached the upper trigger point, and then the whole thing was switched off. And the time this takes depends the length of the impulse, and is also representative for the strength of the magnetic field. Now let's wait a moment. You can see the reference measurement. Now it's over, and now this is the delay time running down, and now it's released, and this was the measurement done. And now I will apply again my magnet here, and you can see that the charging of the capacitor varies tremendously when I apply this magnet near to the pickup coil. And what you also will see is that the when the signal becomes too, the magnetic field becomes too strong, then the system will be overdriven. So now you can see I just prevent the capacitor from fully charging by the strength of this field. Now I'm moving a little more away. And now the capacitor is charging more, and I'm moving more away with my magnet. And now measurement is finished. So this would have been a very long impulse because the strength of the magnetic field was so tremendous. Now we'll change the polarity of the magnet by just turning it, and you will see that the voltage now will have the positive effect. Now comes the reference measurement, and now here we go. You can see now the signal still is overdriven. Why? Because now the voltage here is becoming so low, the base is going so low, that also the collector is going so low that the capacitor is prevented from fully charged. Now I'm taking the magnet a little away, and you can see voltage is rising, and now finally measurement is done. Okay, it restarts now because our impulse was so long that we consumed all the relaxation phase of the trigger unit. Okay. Okay, I hope you gained some interest regarding these results. The next step will be to bring the stuff on a board and bring the circuit into action, and to put all this stuff in a casing, and then doing some experiments with the completed device, and also making a program on my computer to visualize and display the collected data. Okay, I hope to see you again, and bye for now.